Welcome back to some sample problems on forces for AP Physics C. I'm Doug Forrest. I teach physics at Pickerington High School North, and I want to refresh your memory that these are some equations which may prove useful to us when solving forces. Newton's second law, that can be arranged. A is equal to F net over m total, or total mass in a situation. Coefficient of kinetic friction, coefficient of static friction. Oftentimes these resolve into the same equation. Gravitational force near the Earth is mg, and universal gravitational force, which we'll probably use later in the semester, is that. So with this example, we've got a book, and it's hanging here between two clamps. So they're squeezing the book, and there's friction on the book between these two clamps. You might think of it as a normal force in a way, but the normal force is pushing in. So in this case, friction's acting upward, and gravity is going to be acting downward. That's pretty complicated. So I think what we're going to want to do first is figure out a free body diagram. The reason for that is we're going to try to find the maximum mass of the book that can be held if we have this coefficient of friction of 0.80. And this force is applied to each side. So if I look at something like this, I know that the mass of the book is acting downward. So I could think of this as F grav. You could also label that as mg. You should not just say it's gravity, because it's unclear whether you're talking about a gravitational acceleration, a gravitational force. So always label this as a force of some sort. Next, we know that on the book in this case, this particular clamp is actually pushing to the right. So I could say that that's acting actually as a normal force. You could think of it as an applied force also, but it's perpendicular, so it's actually acting as a normal force. I've got the same thing acting over here. So this is pushing to the left. So I've really got two normal forces acting on that book. What's acting upward to keep it from falling down? In this case, that's friction. If you look at this surface, the surface here and the surface here, actually friction acts parallel to that surface. Remember, a normal force acts perpendicular and a frictional force acts parallel to a surface. So the only parallel directions to these vertical surfaces are down and up. So in this case, friction actually has to act upward. Now the way the AP is going to want you to think about that is to draw each individual force and not components. So because there's going to be a frictional force on this side and on this side, I've got to draw two arrows, and they normally will give you a really big dot to do that. So I'm going to say a friction over here and a friction over here. Now, this says this is 0.80 coefficient of friction. If you had a greater coefficient of friction on one side than the other side, these two arrows might be a different length. But as such, each of them should be half the length of the gravitational force downward. So I think that's my completed free body diagram. The next thing I want to do is essentially find the mass of that book. So I'm going to go back and think about an equation again. And if this book is not moving, then I'm going to have the summation of the horizontal forces as 0. Well, we know that's 6 newtons and that's 6 newtons, so that's nothing new to us. So I'm going to actually think about the equation for vertical forces. So I'm going to say force up equals force down. The force up is equal to 2 times the frictional force acting on any one particular spot. So I could say F of F plus F of F. The downward force is mg acting on the object. So I could say 2 force of friction is equal to mg. Well, how do I find out that force of friction? I've got to go back and I've got to think about the equation that I showed you earlier, which is that the coefficient of friction is equal to force of friction over the normal force. Now, in fact, that's greater than or equal to the normal force, but many times we think of these as being equal because we're looking for the maximum amount of static friction. So in this particular case, I could say 0.80 equals the normal force equals the frictional force over 6.0 newtons. So 6 times 0.8, we could say that the normal force is 6. So the frictional force on each side is 4.8 newtons. You could have done that a couple other ways, but I like being consistent with the fact that right now we're only calculating one of these two forces. So I'm going to go back and I'm going to say that 2 times 4.8 newtons is equal to mg. And g can either be 9.8 or 10. Doesn't really matter according to the AP. I'm going to end up putting 9.8, because I'm a little OCD about that. 9.8 newtons per kilogram. So we're going to have 9.6 divided by 9.8. Notice the units, newtons on top, newtons per kilogram in the bottom. So something in the denominator of a denominator becomes a numerator. That agrees with the units I want, which is for mass, which is in kilograms. So I ended up solving for this as about 0.98 kilograms. If you use g is equal to 10, you would have gotten this as 0.96 kilograms. Again, hope that helps. And don't forget, the magic word for Mr. McChesney is candy. Welcome back. Going through sample 3 here for our forces examples. In this case, we've got what's known as a modified Atwoods machine because it's over a pulley. We've got an object called MA, mass of A, an object MB, mass of B. We're going to make some assumptions up here. First of all, the coefficient of friction is 0.20 with this surface and this block. Next, the initial motion we're going to assume could either be at rest or to the right and down. We've got a massless, frictionless pulley. That won't always be true this semester, but for right now it is. And then we've got a light string. Your key in terms of that vocabulary word is if you have a light pulley or a light string, the AP wants you to assume that it's massless, and that's going to help you out. What do we want to find? We want to find the acceleration of the system in terms of MA, MB, and fundamental constants. This is very similar to how the College Board would want you to find things on AP exams. They like variables because it allows you to solve for things universally. And then if you're given numbers, like down here where I'm telling you that mass of A is 20 kilograms and mass of B is 10 kilograms, that essentially what we can do is plug this universal equation in for any specific numbers and get an answer. And then finally, we're going to figure out the tension in the rope, and we're going to use these numbers to do that. So first of all, I need to think about acceleration. I'm going to go back to the master equation of all Newtonian physics, and that is Newton's second law. I'm going to say A equals F net, and I'm not just going to put mass, I'm going to put M tot, standing for total mass of the system. So in this case, we want to look at something that's going on. It might be helpful to draw free body diagrams for both of these. If we look at this, we know that we've got force of gravity acting down, tension acting upward. If this is going to accelerate down and to the right, and this to the right, that means the force downward is going to be greater than the force upward. In this case, on MA, we've got a force to the right caused by the tension in the string, and we've got a force left caused by friction with this surface, since friction opposes the direction of motion, and I told you that the object was going to be moving to the right. Well, if you look at this whole system, the tension upward on B has got to be the same as the tension to the right on A. And in fact, those are acting in opposite directions, even though they don't necessarily look like that. If we straighten this out, we could see that this is really part of the same system. And that tension is an internal force, and using a Newton's third law action-reaction pair of forces, or an interactive force pair, we know that that would not affect the motion of the system. It's only external forces that affect the motion of the system. So really, since the table's gravity is acting down on A, but the normal force of the table is acting upward, we can negate that as well. So what we're looking at here for the net force is gravity acting down on B and friction acting against the motion or the acceleration acting on A. So I'm going to say F grav on B minus F friction on A. That's my net forces. And then in terms of the mass of the entire system is MA plus MB. So now when I go to the next part of this, how would I find the gravitational force on B? That's going to be MB times G. I can't use 9.8 or 10 because this tells me that I need to use only fundamental constants and these mass symbols. Well, G, acceleration due to gravity, is a fundamental constant. What about this one? Well, I know that the frictional force on an object is equal to the coefficient of friction multiplied by the normal force. So I could say mu ma times g. Why mag? Well, that's the weight of the object acting down, but I said earlier that the table's acting up with the same amount of force since ma is not accelerating toward the heavens or down to the center of the earth. So although this represents the gravitational force, mathematically it's the same as the normal force acting on object A. So I actually think that's it. That's not a fundamental constant necessarily, I guess. I could put 0.8 there. That was a little bit unclear. Probably I should have put down here mu as well. So for the next part, I want to get numbers for this. Well, MB is going to be equal to, I said 10 kilograms. I'm going to use 9.8 newtons per kilogram for the gravitational acceleration. You could use 10 as well. Minus 0.8. MA is 20 kilograms. And again, 9.8 newtons per kilogram. And all that over 10 plus 20 kilograms. So when I look at that, I end up with, this is 98 newtons. This is going to be 196 times point. Oh, I think I screwed up here. Yikers. Yikers. That is not what I want to do. I said this was 0.8, but I said up here it was 0.2. So it didn't make sense to me that that would have a negative force. That would mean this would be slowing down. That can happen, but I didn't have that in this particular case. So I need to go back, but this is 0.2. So this is going to be 98. Now this is going to be 196 times 0.1 is 19.6. So double that is 38 or 39.2. Let's go to 58.8 newtons, 30 kilograms. It's going to be a little under 2 meters per second squared. And again, answers be slightly different if you use 10 for G. The last part of this is to find the tension. So the key thing with finding tension in a situation like this is to pick a smaller subset of the system. So that way the tension is acting as an external force. It really doesn't matter in this case whether you pick object A or B, as long as you're consistent with how you do the math. So I'm going to erase this at this point in time so I can do the work over here. And I'm going to go ahead and pick mass B. So I'm thinking about mass B now. I'm going to leave it to you to go back and do the same mathematical calculations that I'm doing, or similar ones for mass A. You should end up getting the same answer. So I'm going to go back to the master law, Newton's second law, but I'm going to do it only for the system. So I'm going to say F net is equal to M system multiplied by the acceleration of the system. Well, in this particular case, I've got F grav down on B minus the tension up here. And that equals mass of the system, which is mb, times the acceleration, which is a. Well, I know a lot of these numbers already, right? I know the force of gravity acting on B is going to be 98 newtons. The tension is what I need to figure out. This is 10 kilograms. That was given to me as 1.96 meters per second squared because I just figured that out. So I get 98 minus T is equal to 19.6 newtons. I end up getting, when I do some rearrangement here, T is going to equal to 78.4 newtons. If I figured this out for A, I do the same thing, except now I've got MA. I've got tension acting to the right, which would cause the positive acceleration, I guess I would say, and friction's acting to the left. So I would have tension minus force of friction on A equals MA times acceleration. And I go through and solve it, and I would end up with 78.4 newtons.